Okay, good morning. The sign-in sheet is going from the back of the room to the front to make sure that you sign in before you leave the lecture today. There's a homework's due on Wednesday. I'm pretty sure that some of those problems will make more sense after today's lecture. If you still have questions, I'll be in my office from 3:30 to 5:30 today. If you cannot go to my office and you need to see me, please send me an email so we can schedule a different time. The problems that are due on Wednesday are in the homework. However, there are some extra problems that I really recommend you to work on. Those are not, you don't have to submit those, but those are going to help you to study for the exam and also to have a better understanding of the concepts. Okay, so even though they're not in the homework, it's very important for you to go and look at the book and try to solve those problems. I'm going to post the solutions for all the problems, including the ones that you don't have to submit, but try to work on those problems anyway. Okay, try to work on them without looking at the solution, even though you're going to have the solution. So again, homework is due on Wednesday. And today what we're going to do is to finish chapter number 2 from your textbook, the lecture on probability. So this is part 2. We started this part on last Wednesday. Any questions, comments before we get started? Okay, so let me go through the slides that we cover on Wednesday. Keep in mind that we are looking at the probability concept at this point. We started with a discussion of the statistics, measure of locations, measure of variability. But right now we're looking at the probability area. So we started defining what is a sample space, what is an event. Now we're focusing our efforts on discussing how to count the number of outcomes within a sample space, and also the number of outcomes that you should expect within an event. Okay, because sometimes you're not going to be able to list all of them, but you still need to know how many of them are available, or how many of them are in your sample space in order to compute the probability of a specific event. So today we're going to transition from the counting to the probability of an event. So we talk about counting samples points and why are important. We talk about the multiplication rule and when that rule applies. And again, these rules apply when you have an operation that can be performed in N1 different ways, and then you have a second operation that is performed on N2 different ways, and so on. So for such cases, you can multiply the number of operations for each different event, and you can get the total number of outcomes for your sample space. We talk about permutations, and basically a permutation is an arrangement of all parts of a set of objects, and you're taking into account the different orders. Okay, so AB is not the same as BA. Okay, so when you take into account the order, that's also a different outcome in your sample space. So we use permutation to count the number of arrangement of these objects. So we talk about several examples, starting with this one, which is very simple. Then we also thought that the number of permutations for n objects is equal to the n factorial, and we discussed what the n factorial is. And the notation that is used for the n factorial is this sign. So we covered a couple of examples, and I think this is the last example we talk about. This is the example we were trying to see how many combinations to accommodate these two representatives of this class. And we talked about these 4 different items, and the number of outcomes depending on the specific situation. Thank you. So again, the number of permutations of n objects is n factorial, but now we're going to discuss different type of scenarios that we can have and how those scenarios can be combined into different expressions in equations. So this is the first one. Permutations that occur by arranging objects in a circle is called a circular permutation. So for example, if 4 people are playing bridge, we don't have a new permutation if they all move one position in a clockwise direction. So by considering one person in a fixed position and then arranging the other 3 in 3 factorial ways, we find that there are 6 distinct arrangements for the bridge game. So again, if you have an arrangement in circular way, the number of permutation of these n objects is always equal to n minus 1 factorial. Another type of permutation is this one. And again, as I recommended you last time, it's very important for you to keep track of these different theorems. So when you look at the problem, you can see which theorem will apply to that specific situation. So this is theorem 2.4, and this is for the number of distinct permutations of n things, of which n1 are one kind, n2 is of a second kind, and k is a k different kind. So you have different objects, different type of objects, and you're trying to find this number of outcomes for these n different objects for different classes. So let's look at this example. Using the football game, the college football game, training session, the defensive coordinator needs to have 10 players standing in a row. Among these 10 players, there are 1 freshman, 2 sophomores, 4 juniors, and 3 seniors. So again, these are different types, well, not different types of students, but different classification of students. Okay? Sophomore, junior, freshman, and seniors. So the question is, how many different ways can they be arranged in a row if only their class level will be distinguished? So again, we have different number of freshmen, sophomores, and seniors and juniors. So what we can do is, we know how many players we have, right? So n equals 10. So the total number of students are 10. And we know that freshmen is 1, sophomores 2, juniors are 4, and seniors are 3. So the question is, again, how many different ways can they be arranged in a row? So 10 students, and you have this number of different classifications and different amounts for each classification. And you want to know what are the different combinations that you can create by only taking into account the type of, or the level, or the class level of the student. So if we use the theorem 2.4, which is exactly the same situation that is happening in this problem, we can use this expression to compute the number of outcomes. So what you do is just look at the total number factorial divided by n1 factorial, n2 factorial, n3 factorial times n4 factorial. In this case, that is 10 factorial divided by 1 factorial, 2 factorial, 4 factorial times 3 factorial. And the number of different permutations is 12,600. So by having that limited amount of each class, you can see that you still have a lot of combinations. Okay, and there's no way over. And you will spend a lot of time trying to come up with this number of combinations. But still, you need to know the number of outcomes when you try to compute the probability of one of those outcomes to happen. Okay? So this is one type. Again, we are looking at the different number of permutations for different classes. Now let's look at a different type of problem. So often we are concerned with the number of ways of partitioning a set of n objects into R subsets, which are called cells. So we have, let's say we have 100 students and we want to separate them on different classes. So we want to know what are the possibilities of splitting these students in these certain number of classes, depending, let's say, on the courses. So we have different courses, so we want to know how to put the students into these courses. So partition has been achieved if the intersection of every possible pair of the R subsets is the empty set, and if the union of all subsets gives the original set. So remember the concept of intersection and union. Okay, so intersection is empty. That means that there's no overlapping into these groups, to these subsets. And the union, basically, if you put them all together, you have the total number of units. So using this theorem, the number of ways of partitioning a set of n objects into different cells with n1 elements in the first set, n2 elements into the second one, and so on, is the same expression, but now we're using a notation to denote this type of problem. So we have n over n1, n2, up to nr, and we know that the sum of these sets or partitions is going to be equal to the total number of outcomes or units. So using this concept, we can look at a different example. So now we have 7 graduate students, and we have 2 rooms, 2 hotel rooms, and we want to know how many ways we can put these 7 graduate students or assign these 7 graduate students into these triple and double hotel rooms during a conference. So we want to save money, and we want to put all these students in the less number of rooms possible for this conference. So again, we know the total number of students, which is 7. We know that we have 1 triple room and 2 double rooms. So one of the sets will have 3 and the other 2 will have 2. So we want to know how to arrange, or how many possibilities we have to arranging these 7 students into these 3 sets or subsets or cells. 1 with 3 capacity, and 2 with a capacity of 2, and then 3 with a capacity of 2. So easy, we use the same notation, 3, 2, 2. And again, you look at the total factorial divided by factorial of 3 times the factorial of 2 and the factorial of 2. And for these 7 students in these 3 rooms, we have a different 210 different options. Okay? So again, we are looking at the total number of units and want to put them into cells. These are the possible combinations or options, 210. Any questions? Okay. So now in many problems, we are interested in a number of ways of selecting R objects from N without regard to order. So now we have a number, let's say 100 units, and we want to select from those a R number, let's say 20. These selections are called combinations. So the important thing here is that now, for this type of problem, we are not taking into account the order. Okay, so for permutations, we were taking into account if AB is different than BA, CA is different than AC. Right now, for this type of problem that we're going to discuss right now, the order is not important. Okay? So, theorem 2.6, saying that the number of combination of n distinct objects taken r at the time is equal to n factorial divided by r factorial times n minus r factorial, where r is the number of units that you're selecting from the total. Okay? So let's see how this applies to a real problem. Okay, so this was a problem that I basically updated. This young boy was asking his mother to get a 5 PS Vita cartridges. They were talking about Game Boy, so I think Game Boys right now are not produced anymore. So PS Vita, I found out that it's the latest game console that you can take any place. So let's look at the PS Vita. 5 cartridges for his collection of 10 arcade and 5 sport games. So how many ways are there that his mother can get 3 arcade and 2 sport games from this collection of 10 and 5? So again, we're going to look first at how many ways are there that his mother can get 3 arcade first. Okay, so we know that we have 10 arcade and we want to select 3 out of the 10. And we want to know how many options do we have. So the question is the number of ways of selecting three arcade from 10. And again, once we select one, we are not putting that one back into the group. So we're going to have less options. We're going to have 9 to select 2, 1 to select 8. The other way around, 8 to select 1. Okay? So based on the theorem 2.6, we want to know how many options to select 3 out of 10. And that is equal to n factorial divided by r factorial times n minus r factorial. So this is 10 factorial divided by 3 factorial times n minus r. So this is 10 minus 3 factorial. So for this case, we have 120. That's only for the arcade. Now we need to look at the sport games. So we do the same thing. The number of ways of selecting two sport games from 5. So in this case, we have 5 to select 2, and this is 5 factorial divided by 2 factorial times 5 minus 2 factorial, and that is equal to 10. So again, look back to the question or read the question again. How many ways are there that his mother can get 3 arcade and 2 sport games? So far what we have are the chance or the possibilities for selecting the arcades independently of the sport games. Do you know or have an idea of how to answer this question that is taking into account both at the same time? Yes. You can use the multiplication rule to find the number of possibilities for selecting 5 out of 10 and 2 out of 5. So using the multiplication rule, this is rule 2.1 with N1 equals 120 and N2 equals 10, then we can have 120 times 10, which is 1,200. So you can see how this number goes up, and we are looking at the very, very small problems, just standard case, and you have to select 3 and 2 out of 5. So by looking at that small sample, you'll still have 1,200 different combinations. Okay? Let's look at the next example. Can I go to the next slide? Okay. So this problem is a fuel economy study. Each of 3 race cars is tested using 5 different brands of gasoline at 7 test sites located in different regions of the country. If 2 drivers are used in the study and test runs are made once under each distinct set of conditions, how many test runs are needed? So you see, right now we have multiple combinations, multiple options. So let's start with the number of race cars in 1. We have how many? 3. So these are race cars. Then we also have 5 different brands of gasoline. So N2 equals 5. This is gas. We have 7 test sites. So N3, 7 test sites. And what else? And 4 is the number of drivers. 2, right? Two drivers. And that's all we have. So we have N1, N2, N3, and N4 different options for each category. And the question is, test runs are made once under each distinct set of conditions. How many test runs are needed? So we have 3 factors for the first one, 5 factors for the second one, 7 factors for the third one, and 2 factors for the last one. So if you're going to combine all of them, what rule should you use? So again, those factors are independent, so we can use the multiplication rule in order to find the total number of test runs. So the multiplication rule yields 3 times 5 times 7 times 2 equals 210 test runs. important for you to go back and review these problems. So that's the only way that you will get familiar with the different scenarios and how to implement each type of combination, permutation, or rule. Okay, so I think, let me do something. On the next slide, we are transitioning to the probability of an event. But before we get to that point, let me just list the most important rules. So rule 2.1, again, is the multiplication rule. Two is theorem 2.1, and that is to compute or the number of permutations Permutations are arrangements or possible orders. Of n objects. So if you have a problem that asks you to find the number of combinations or arrangements, possible orders of this certain amount of outcomes, then you go find theorem 2.1 and find out what to do. We also have theorem 2.2. This is for the number of permutations of n distinct objects taken r at a time. And you remember this notation, NPR equals n factorial divided by n minus r factorial. And here the order is important. So that's theorem 2.2. I'm going to skip the circular permutation. That one is not used that often. I'm going to go to theorem 2.4. So theorem 2.4, number of permutations N1 are one kind, N2 second kind, and so on. So this is n factorial divided by n1 factorial, n2 factorial, n3, and k. In the same way, theorem 2.5 is to select the number of ways of partitioning a set of n objects into R cells. And the last one, and this one is the same, n factorial divided by n1 factorial, n2 factorial, n3, and k. And then we have theorem 2.6, which is the number of combinations of n distinct objects taken R at a time, and here the order is not important. So nr equals n factorial r factorial times n minus r factorial. So you see these two expressions are very similar, this one and this one. The only difference is that this one does not consider the order, and for this one, the order is taken into account. Okay? So 2.2 and 2.6 are similar. What should you expect in terms of the number of outcomes? Would you expect this one to have more outcomes than this one? Yes or no? And if the answer is yes, tell me why. The answer is yes. If you take into account the order, then you know that you're going to have more combinations because A, B is not the same as B, C. And when you take into account the order, then you need to take into account those two combinations as two separate combinations. But when the order is not important, that one accounts just as one. Okay? Is that clear? Okay, so my recommendation again, go back, review these theorems, the examples, and if you understand this, pretty sure that you're going to do very well in the exam. You're going to do very well in this course, and you will do the homework very easy. Okay? If you don't understand, I don't expect you to get this right away, but if you have questions, always go to my office or talk to me at the end of the lecture. Okay? These are not, I mean, it looks easy, but those are not easy concepts. And especially if you don't have any probability background or statistics background, it takes some time to understand and to finally be able to differentiate between them. Okay, so again, go back, read, let me know if you have questions. For now, we're going to transition to a new topic, which is the probability of an event. So right now, we understand how to list the outcomes for a problem, the number of options. So what do we do with that? Why is that important? The important is right here. Now the number of outcomes, you can compute the probability of one of those outcomes to happen. So probability of an event, to find the probability of an event A, we sum all the probabilities assigned to the sample points of this event A, and this sum is called the probability of A, and is denoted by this P given A. Okay, so if we put P and the event into parentheses, that means that we are looking at the probability of that event to happen. Then we have a definition. So if you sum all the probabilities of the outcomes of this event, do you have an idea of what is the number that you should get at the end? You have probabilities of all the outcomes. So you have 5 outcomes and you sum the probability of each one of those outcomes. What is the total of that summation?
1%.
1. Okay? Probability never should be more than 1. 1 means 100%. We have a probability that is 100, 1.2, 120%, something's wrong. Okay? And if you are adding all the events, together and your summation, or all the outcomes of an event together and your summation is not 1, something's wrong. Okay, so here's the definition of a probability of an event. So again, probability of an event A is the sum of the weights of all the sample points in that event. Therefore, probability of A is always within 0 and 1. The probability of the empty set is 0 because you have no outcomes. And the probability of the sample space, where you have all the outcomes, is always equal to 1. Always equals 1. Okay? So if A is the event, and A is the same as the sample space, you know that the probability should be equal to 1. Okay? So furthermore, if A1, A2, A3 is a sequence of mutually exclusive events, then the probability of the unions is the summation of the probability of the events. So let me show you with the picture what that means. So if you have, anyone remember what mutually exclusive is? No overlapping, right? If you look at the Venn diagram, mutually exclusive, no overlapping. So if we have such type of equations, then we can find the probability of those mutually exclusive events by just adding them. Because there's no overlapping, there's no intersection, no duplication of probabilities. Okay? So let's look at this problem. And again, I'm using this problem because it's one of the problems in which you can list the sample space very easy and you can understand the concept right away. So we are looking at the coin that is tossed twice. What is the probability that at least one head occurs? So you're using one coin and you're tossing that coin twice. So what is your sample space? How many outcomes you should expect? Correct, it's 4. And the sample space is just these 4 events in which both of the coins are head. One, or the first one is head, the second one is tail. The first one is tail, the second one is head, and 2 tails. Those are the only combinations that you can have. That is your sample space. Okay? The question is, what is the probability that at least one head occurs? So you have your sample space, you know those are the outcomes, all the possible outcomes. But now you want to define an event from that sample space. And that event is the probability that at least one head. So there's one outcome there that does not satisfy that condition, which is this one. Because there is no head in that outcome. So let's define that event. So I'm going to call that event A. And you have head, 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 tail, tail, head. Okay, so that's my event. Those are the only outcomes in which the head occurs. So now what is the probability that at least one head occurs? So if we assign the same weight to each outcome, we can say that we have, from the sample space, we have 4W equals 1, because we know that the probability should be equal to 1 always. So each outcome should have a weight of 1/4 or a probability of 1/4. Okay, we're looking at the sample space. If we assume that the coin is a pair coin, then we can say that each flip has the same probability of being head and tail. So each outcome has a probability of 25%, 1/4. Okay, so all of them have the same weight, meaning that had the same chances of being observed. So now using A, A again is the event at least one head occurs. Then what will be that probability? 3/4, correct, 0.75. Why is that? Because our A is defined by TH. Each one of them has probability of 1/4, so the summation is 1/4. That's 3/4. So you have a 75% chance of observing at least one head in your experiment. Any questions? Okay. Okay, so basically this is a summary that what we just discussed. If an experiment can result in any of the n different equally likely outcomes, and if exactly n of these outcomes corresponds to an event A, then the probability of an event is just the number of outcomes that satisfy that event divided by the total number of outcomes. Okay? Now let's look at this example. Statistics class, just like this one, for engineers consists of 25 industrials, 10 mechanicals, 10 electricals, and 8 civil engineering students. If a person is randomly selected by the instructor to answer the question, find the probability that the student chosen is an industrial engineering major. So let's say I select you. What is the probability that he is from industrial engineering based on these numbers? I mean, I'm not asking him, I'm just trying to put you in the scenario. That's correct. Okay? So, what do you do? We have industrial, we have civil, we have electrical, and we have mechanical. So the total, that's the first thing that you need to find out. Total is 25 plus 10 plus 10 plus 8 is 53. So that's your sample space. You have 53 students. And you want to know, if you select one at random, what is the probability that that student is an industrial engineering major? Okay, so from a total of 53, you know that you have 10 that are industrial. I'm sorry, it's 25. 25 that are industrial. So your probability is 25 over 53. Part B. What is the probability that the student is either civil or electrical? Say that again. 18 over 53. Anyone else? That is correct. So, anyone can tell me what this, in terms of the probability terminology, what this means? Civil or electrical? Is that a union or intersection? It's a union of events. And you know that when they are independent, the union of events, you just add them. So that's what we're going to do. So the probability of C union E will be equal to 8 plus 10 out of 53. And that is 18 over 53. Any questions? Now some of you are from the electrical engineering program and have taken a course that have discussed these type of concepts already. So I know you have an advantage. But again, simple concepts, you need to go back, review, or to grab them. Okay. Let's move to the next. So now let's discuss additive rules. So again, I know theorem 2.7, if A and B are two events, and the union, these two events are not mutually exclusive, such like this case in which you have the intersection of both events, then the probability of the union equals the probability of A plus the probability of B minus the intersection. And you need to take that minus the intersection, because if not, then you're going to count that space twice, because you have that space for A and that space for B. So if you're going to have these two events, this is the equation or expression that you need to do. Probability of A union B equals this. Now, we have a corollary here, 2.1, and when you know that they're mutually exclusive, then you don't have to take into account the intersection, because there's no intersection. Okay? And the same rule applies for multiple events. So let's say you have more than one event, then if they're mutually exclusive, then you don't have to take into account the intersection between the events. If you want to find the probability of all the events, just add them separately. And again, this is just when they are mutually exclusive. Mutually exclusive, let's draw a picture. So you have your sample space and the events do not overlap. In this case, previous case, overlapping, you need to take into account the intersection. When there's no overlapping, you don't have to take into account the intersections. Now, let's say we have three events and they are not mutually exclusive. Then the expression gets a little bit bigger. You have the summation of the three events. You have the subtraction of the intersection of each combination plus the intersection of the three. So this is for the case in which you have this. A, B, and C. So if you subtract this intersection, you subtract this intersection, and you subtract this intersection, then what happened is that you will not have this part of the probability in your expression. So that's why when you subtract these 3 times, you need to add back this portion. Okay? So that's when 3 events, when you're taking into account 3 different events, or 3 events. Any questions? Okay, so another example. What is the probability of getting a total of 7 or 11 when a pair of dice is told? Any idea? Let's look at each one of them independently. So let's look at A, and let's call this one the event that 7 occurs. So if you have to list the number of outcomes in which that event will happen, You have 6 and 1. You have 1 and 6. You have 5 and 2. You have 2 and 5. And then you have 4 and 3 and 3 and 4. Those are the only outcomes that can happen. Let's do the same thing for event B. Event that 11, of course. 6, 5, 5, 6. Those are the only combinations. So you have 6 outcomes for the first one and 2 for the second one. What is the total number of combinations if you take into account all the numbers? Correct, 36. So you have 6 for the first one and 6 for the second one. And we'll use the product rule, that is 36. So if you were to list all of the possible outcomes, you have 36 outcomes. So you need this number, you need this number and this number to compute the probabilities. One more time, you need a total, you need the number of outcomes for that particular event, and the number of outcomes for the other event. So the probability of A is 6 over 36, which is 1/6, and the probability of B equals 2 out of 36, 1 over 18. Are we done? Yes, sir.
How did you get 36 again?
36, you have 2 dices, right? And you have 6 outcomes for one and 6 outcomes for the second one. So those are independent. So using the product rule, 6 times 6, 36. Good question. So this is using the product rule. I believe it's 2.1. So the question is, what is the probability of getting 7 or 11? Not just one of them, but one or the other. Are these events mutually exclusive? Independent? Why? Because there's no way that you can get a 7 and 11 at the same time. Okay, you can get 11 or 7. So that makes the event mutually exclusive. The other way to see it is, if they are not mutually exclusive, then you will see one of these outcomes repeated in both events. But there's no outcomes repeated. So they are mutually exclusive. So what happened? We learned something a few minutes ago. They're independent, mutually exclusive. So since A and B are mutually exclusive by corollary 2.1, we know that the probability of A union B is equal to the probability of A plus the probability of B. In this case, that is 1/6 plus 1/18. 4 over 18 equals 2 over 9. So as you can see, for a simple problem like this one, we are using different concepts. So first concept is to find the total number of outcomes for such experiment. So we are finding the number of outcomes for the sample space without listing all the outcomes. So that's the first thing. Product rule, find the number of outcomes of your sample space. And remember, what we're trying to do is to get to the probability of a particular event. So we need the number of outcomes, 36. Now, we need to define each event independently. We find the number of the outcomes for each event. Okay, so in this case, we list them. So we found for event A, 6 outcomes, for event B, 2 outcomes. So now we are ready to compute the probabilities based on the event. So event A, we have 6 out of 36. Event B, 2 out of 36. Now we have the probability for each event. But what happened? The question is not for each event, it's for one or the other. So now we need to look at the union. So the union tells us that if they are mutually exclusive, you can add the probabilities. So we add the probability, and finally we get the result. Okay, so for a simple problem like this, you are using 1, 2, 3, 4 different concepts. Okay, so it looks easy, but you need to understand what do you need and how to get that information. So again, very important for you to understand what we are trying to do, because we're going to keep adding more information into these problems. Let's look at another example. Okay, so if the probabilities are respectively 0.9, 0.15, 0.21, and 0.23, that a person purchasing a new car will choose the green color, white, red, or blue, what is the probability that a given buyer will purchase a new automobile that comes in one of those colors? Are these events mutually exclusive? If you buy a car that is green, you cannot read red or yellow or any other car. So those events are mutually exclusive. Okay? So we identified that they're mutually exclusive. So we know that the question is asking what is the probability that a given buyer will purchase a new automobile that comes in one of those colors. So this is an and or an or. Basically what I'm trying to find out is, are you trying to find the probability of the union here of this event? So the 4 events are mutually exclusive. So using theorem blank, we can compute that probability. So the question is, I want to know what is the probability that someone will come to the dealer and buy a car from one of these colors. So in that case, you are looking at the union of the events, because it could be this one, this one, this one, or this one. Okay? So when we have that type of problem, so here is the probability of green, union, W, union, red, union, blue. So using theorem 2.7, we know that they're mutually exclusive. The only thing that you need to do is to add the probabilities. .09 plus 0.15 plus 0.21, 0.23. Mutually exclusive, we identify that we are looking at the probability of the unions of the event. The only thing that you have to do is to add those probabilities. Yes, sir. Yeah, I think I'm running out of battery. Hello? Can you hear me? Okay. Maybe it's reception here. Okay. So again, the unions of events, we have different events that are mutually exclusive. And we are trying to find the probability of the unions of those events. So we have a concept or a theorem that we already discussed that says that when you are looking at the union of the events, that the mic is not working. It's running out of batteries. So when we have that type of problem, we can just add the probability of the independent events or the events by themselves and get the probability. Any questions? Okay. Now we have a very simple but interesting problem. This is a concept that is very important again. Simple but important. So again, the summation of the probability of all the outcomes of the sample space is always equals 1. Remember that. So if you know the probability of an event, you can find the probability of the complement by just subtracting 1 minus the probability of that event. Does that make sense? You know that the probability of A is 0.75, and you know that the complement of A will complement the sample space. Then the only thing that you need to find is, for the probability of the complement, is that 1 minus the probability of that event. And that is called the complement. Okay? So we're going to use this concept in this problem right now. So if the probability is that a car mechanic will service 3, 4, 5, 6, and 7, or 8 or more cars on any given workday are this: 0.12, 0.19, 0.28, 0.24, 0.10, and 0.07. What is the probability that he will service at least 5 cars on his next day at work? So we are interested in the probability of at least 5 cars. So the event that we are trying to define is those days in which you will service 5 or more cars. So we can solve this in different ways, but I'm going to use the complement to show you the concept. Okay, so again, the probability of this event is equals to 1 minus the probability of the complement. So we know that for most of the days, if you look at these numbers, for most of the days, this mechanic will serve 5 or more cars. So we can use the probability for those days in which he will not serve more than 2 cars to find this probability. And those cases are when he serves 3, that's 0.12, and when he serves 4, that is 0.19. Let me list all of them. So 5, 0.28, 6, 0.24, and 7, 0.10, 8.07. Okay, so there's 2 ways that you can find this probability. You can just add these 4 numbers, 0.28, 0.24, 0.10, and 0.07. That will give you the answer. Or if you are lazy or a little bit you understand the concept, then you can just subtract from 1 these two numbers. So 1 minus 0.12 minus 0.19, and that will give you 0.69. Same thing, if you add these numbers, you will get 69. So you can solve the problem directly, or you can use the concept of the complement. Subtract these two numbers from 1, you'll get the same answer. Questions? Okay, so I have one more problem for today, and I think that's the last thing I'm going to do. This problem, so here we have an industrial type of problem in which we use a filling machine for filled boxes of product. This occurs in the food industry as well as other areas in which the product is used in the home, for example, detergent. As you know, machines are not perfect, so there are some events that can happen. For example, event A is when you fill to specification, B is when you're underfill, and C is when you're overfill. The general practice of underfilling is that which one hopes avoid. So we don't want to underfill to sell to your customers. And we have some probabilities here. The probability of happening underfilling is 0.001. And we have the probability of filling to a specification 0.990. I have a video for if you haven't seen something like this. Let me see if this works. Sometimes if you run out of your raw material, you need to set up the machine again. So once you set up the machine, it takes some time to have the machine running to what you expect. So that could be an event. Or machine failure, maintenance required, could be several things. The operator does not know what he's doing. So multiple things, yes. So that's a good question. So we have those probabilities, right? And the first question from this problem is to find the probability of C. And C is the event of overfilling. So we learned something just 2 minutes ago that can help us to solve this problem. So we know the probability of A, the probability of B. So in order to find the probability of C, what would you do? Yes. So you look at the complement. So you know the probability of, oops. So the probability of A plus the probability of B plus the probability of C equals 1, right? So if you know A and B, you can find C. So A, probability of C equals 1 minus the probability of A minus the probability of B. And that will be equal to 1 minus 0.990 minus 0.001. Questions? Part B. What is the probability that the machine does not underfill? That will be either fill to specification or overfill. Does that make sense? Right? Because you know the probability of underfilling, so the complement of that is the probability of not happening that event. Part C. What is the probability that the machine either overfills or underfills? So once you see these four, that means that that's a union of events. So you have probability of B union C. And since they are independent or mutually exclusive, you can add them. So this will be equal to 0.001 plus 0.009, 0.010. Any questions? Okay, so that's all for today. Remember the homework on Wednesday. And remember, we're going to have our first exam 2 weeks from today. So just wanted to let you know for you to start preparing. Okay? One second.